In this video, we present a new class of volumetric displays that use a two-dimensional light engine and a three-dimensional indexable point cloud to display 3D content. Here we see the basic optical design used in all our implementations. The light source is a 1024 by 768 pixel digital projector. A planar mirror is used to fold the optical path of the projector to reduce the physical size of the light engine. The diverging rays from the projector are converted to parallel rays using a Fresnel lens. The rays from this orthographic light engine are used to illuminate passive scatterers within a glass cube. The scatterers are physical cracks embedded in the glass cube using laser-induced damage. The advantage of laser-induced damage is that it imposes no restrictions on the structure of the point cloud. It can be regular, semi-regular, or randomized, as in most of our implementations. We first show the display of simple 3D objects using an XYZ dithered fully indexable point cloud with 10,000 points. Here we show a tilted circular disk spinning around the vertical axis. Since it is hard to convey the results of any 3D display using a single perspective, here we show 4 different perspectives of the spinning disk. In this example, we see a sphere that is half red and half green. The sphere is seen rolling and bouncing off the boundaries of the display volume. Once again, we show 4 different perspectives of the rolling sphere. Our second implementation uses a denser point cloud to display extruded objects that have translational symmetry along the vertical axis, and a top layer that can have an arbitrary texture. This point cloud has about 190,000 points. The top layer has about 10,000 uniquely indexable points on a regular grid, and the extrusion volume has about 180,000 points that are Z-dithered. Here we see extruded objects of different shapes being displayed. Notice how the top layers of the oval and square-shaped objects have lids with holes in them. Here are 4 different perspectives of the display being shown simultaneously. This display has been designed for showing purely extruded objects. In the case of letters and numbers, pure extrusion gives the displayed information a three-dimensional feel. This point cloud has 180,000 points that are Z-dithered. Here we see the characters 3D being displayed. The characters are blue in color but have white outlines. Here are the 4 different perspectives of the same content. We have designed a point cloud that allows us to extend the game Pac-Man to 3 dimensions. The point cloud has about 83,000 points and includes horizontal path segments at 4 different depths and vertical path segments between the depths. The ends of some of the horizontal segments have target patches that the player must explode to complete the game. The path segments are displayed in blue and the targets in pink. The location of the player is shown as a blinking green dot. The player uses a joystick to control his or her position in the cube. Here we see the game being played by a person. The third added dimension makes the game more challenging and engaging for the player. Laser-induced damage provides a very simple and fast way of creating customized 3D avatars. In this case, the point cloud simply lies on a surface that corresponds to a human face model. The projection of a face video with expression changes onto the static face cloud creates a very realistic and compelling effect. Here we see 3 different views of the 3D avatar. Note that misalignments between the expressions of the static model and the projected video are not noticeable. We are in the process of incorporating simple speech and vision analysis into the 3D avatar to enable people to interact with it. In this work, we have developed a novel class of volumetric displays that are simple and inexpensive to implement, and yet are very effective in conveying certain forms of 3D content.